Hi, everybody. Okay, now we're going to do our next measurement of the system. We're going to measure what's called the energy relaxation time, or T1. What's this? It's the time it takes for the following. If we excite the system from the low energy state to the high energy state with a pi pulse, it's the time it takes for the energy to leak out of the system so that we end up back in the low energy state. Well, actually, the population in the upper state really decays exponentially. So T1 is actually the time constant for this exponential decay. So how are we going to do that? Well, we're going to be very clever, because it turns out that T1 is going to be much longer than the free induction decay time that you've just measured. So we can't measure it just directly, because after the free induction decay time, the signal has vanished. We have to play a trick in order to do this. And to do that, we'll use what's called a two-pulse sequence. Here's the idea. First, we're going to excite the system from the low energy state to the high energy state with a pi pulse, okay? And then, after some time, we'll excite it again with a pi/2 pulse. If we do this after a very short time, then the state vector will still be in the upper state, and we'll just excite it like that. And we'll end up with all the spins pointing in the same direction. So now the spin state will be the X state. And from here, the spins will start precessing and will give us a large signal, okay? So if we excite it at, with a pi pulse, and then immediately after with a pi/2 pulse, we'll see a big signal. On the other hand, what if we wait a very long time and then do the pi/2 pulse? So suppose we don't do this now, but we wait a very long time. Well, of course, once again, we'll rotate the state vector by 90 degrees, and the system will start precessing. But 90 degrees from this state points in the -x direction, like so. And starting from that point, we'd see a big signal. So if we wait a very long time, we would also see a big signal, but there is a difference, because now the state vector starts out pointing to -x direction. The trick is, what happens if we wait an intermediate length of time? Suppose we wait until the point when half of the population now can be found in the upper state and half in the lower state. If we did the measurement then we get the following interesting thing. The part of the population that was still in the upper state, it would rotate into the +x direction. The part of the system, part of the population that was in the low energy state, it would rotate into the -x direction. And if the initial populations were the same, these will cancel out, because they're vectors pointing in opposite directions, but they have equal magnitude. So at that point, the signal would be 0, or at least close to 0. And in between, we'll see something like this. Signal delay. So there should be a point, a delay value, where the signal is at a minimum value, here. And that's the point where T is equal to, well, it's not quite T1. It's the half-life for the upper state, which is related to T1 in a very simple way. You can figure out. There's a factor of logarithm of 2 in there, but I'm sure you can get it. Okay, let's go take a look at how that works.